Do you guys have questions about last Mathematica session? Functions and patterns? Yes?
You, at the beginning, you defined a function as symbol, bracket, and column equals.
Yes.
Is there any difference if we only use simple equals, or is it just...
Oh, there is
besides these delayed assignment and instant assignment.
What other question, what other difference are you thinking about?
If I say f of x equals y, or something like, or anything. Or, yeah, something. Another definition of phase is called, does it, in this case, does it matter?
Ah, yes, it does matter. It
If I don't use something unknown on the right side.
It does matter, and I can either answer this question now or wait. I guess I can show it now. So let me... Style sheet, report. Okay, 150. I guess we can look at this right away. Later on, I will show many different ways of computing the Fibonacci numbers, but it's a very good example to answer your question. So Fibonacci numbers are those, it's a sequence. It starts from 1, and then it goes 1 again, and then you have to add the previous 2 elements of the sequence. So 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 2 is 5, and so on. And the question is how to compute them, how to write a function that computes them. And we would say something like Fibonacci of, let's say, 0 equals 1, just to initialize the sequence. Fibonacci of 1 equals 1. And then we can have a recursive definition, Fibonacci of n minus 2 plus Fibonacci n minus 1. Okay, so you agree that this thing will compute our Fibonacci sequence. Fibonacci of 6 will be 13. If we continue, 3 plus 5 is 8, 8 plus 5 is 13. So this is doing the right thing. Oh, okay. So this is computing the right thing. I don't want to get into details now, but let's do the following. When I evaluate Fibonacci of n, first of all, I print n, and then I evaluate, okay? I think I told you already, you can use parentheses also to create a sequence of instructions, of commands, as long as you put semicolon. So now, whenever I evaluate Fibonacci of n, I will print n and then perform the evaluation. Now let's see what happens. Fibonacci of 6, I evaluate Fibonacci of 6 once, of course. This calls Fibonacci of 4 and Fibonacci of 5. So here it is, Fibonacci of 4 comes immediately. Then from 4 I go to 2 and so on. And if you see, how many times do I end up calling Fibonacci of 2 and Fibonacci of 3? And even Fibonacci of 4, there is more than, it's called more than once. So basically I am repeating recursive calls to elements, to numbers that I have computed already. Okay? The computation goes through and I end up computing the right thing. It's just that as part of this computation, I recompute the same quantity over and over. Fibonacci of 2, I compute it 1, 2, 3, 4, 5 times, or maybe even 6. And we know that it's going to be just a 2. There is no reason to recompute it all the times. So, to answer your question, we could have something like this. So when I compute Fibonacci of n, not like that, like this, yes. When I compute Fibonacci of n, not only do I compute it, I also store it as a constant. So first, yes, I evaluate it, and then I store it in memory, and I associate it to Fibonacci of n. So let's evaluate this. See what happened? I reduce my the number of recursive calls by a lot. In the previous case, we will add an exponential number of recursive calls. Over here, we have a linear number of recursive calls. Where is the trade-off? Can anyone see where the trade-off is?
First off, the individual function calls get a bit more expensive because the more you store, the more patterns you have to search for your argument. And second, you of course increase the amount of memory you need because you're storing results.
So you see that now my definition of Fibonacci is not just a recursive call, it actually consists of a number of ground, of base values. If I go ahead and evaluate Fibonacci of 16, first of all, it's going to be much, much faster than the pure recursive call. Notice that the lowest call is a Fibonacci of 7. Why? Because the 6 and 5 have been defined already, so I don't have to evaluate them. But now, if I look at Fibonacci again, the definition has expanded. So if we went for thousands, we would have a lot of memory taken by the definition of Fibonacci, but we would have a linear complexity algorithm. So it's a trade-off. So there is a difference. I hope that answers your question.
Not exactly, because now you still set column equal.
Yes.
What if you just say equal? You can use the pattern there too on the left side. So Fibonacci of n equal Fibonacci of n minus 2 and so on.
So what you want me to do is the following. Right?
Yeah, no pattern for n.
Oh, pattern, yes, of course.
Oh.
Man, don't attempt this, right? This is not a good idea. So let me try again. So how can this work? Because the moment since it's a constant, you're going to evaluate Fibonacci of n minus 2 and Fibonacci of n minus 1 right away, immediately. And those definitions are matched. It's a recursive definition. So yes, this does not surprise me. I'm not sure that's a good way of programming.
It did work for non-recursive functions.
So now something like this, it's different. What happens with something like this? So Fibonacci of 5, 3. I'm not sure what to say. Let me think about it, okay? I'll get back to you. Okay, guys, let's go back to our dating experience, we have our third meeting with patterns, underscores, and all of that. So, last week we did a lot, and in just a few minutes I will have a summary, a recap of all the patterns that we have looked at last Tuesday. For now I want to continue talking about constraints, and I will start with our own definition of a factorial function. I want to extend the factorial definition to negative numbers as well as non-integers, so real numbers. So it's time to look at the if statement. I don't think we have ever used it so far. The right way is to always ask Mathematica how to use the if statement, and it says you put a condition, then let's go into the most general scenario. If the condition is true, then Mathematica returns the expression t. If a condition is false, it returns the expression f. If cannot evaluate this condition, if it cannot find whether it's true or false, then it returns the undetermined. Okay, so over here I prepared a factorial definition for factorial, which you would normally use in most of the standard languages. You start off and you say, oh, if n equals 0, okay, that's our base case. Let's return 1. If n is greater than 0, then recursive call. Now, if n is not greater than 0, and it's for sure not 0, then it's negative. And then my definition was, let's invoke the factorial of minus n. This is it. This is for integers. Now, if I want real, it immediately becomes cumbersome. We would have to take the head, the type of n. We did it already. We have to check whether the head is an integer, then we apply this. Otherwise, we apply something else that has floors and ceilings. And it's a lot of if statements, and we don't like if statements. So instead, why don't we do it? Why don't we program the Mathematica way? Let's give the definitions the same way as the problem is defined. So the problem says integer and positive, we want factorial. Okay, so we say if it's integer and positive, then return n times my factorial. This is not an AND. This is an integer. It's a pattern. Then there is a condition, a test on the value. So this positive is a function that operates on whatever is matched by the pattern. Is that a question? No, okay. So vice versa, if n is an integer but it's negative, let's just call my factorial of minus n. Now let's go to real numbers. So now we force the pattern over real numbers, and then I just tested the positivity in a different way. These two things are exactly the same. Over here there is a condition, and what I do is I call factorial on floor. That's exactly what the definition says. And then you can imagine my fact of real but negative is blah blah blah. I don't have any if statements. I don't have strange bodies of functions where I have to browse and try to see which branch determines the definition that I'm interested in. I have very, very clear entries. The function name is the same. I even changed the argument name. I used n to denote integers. I used x to denote reals. These are just little visual cues to help myself. So I don't know, did I evaluate all of these? No. There are way too many. So let's do this. One, two, three, four. Okay. I guess we can Check my factorial. Minus 3.5 is something, 3.5 is something else, 4, 0, and so on. And my fact tells me exactly what my factorial does on different data types. So this is much more elegant than a big body with a case or a switch or if. And also my fact, right, like this, it's only defined for those cases that I did define. Okay, I want to show you how patterns can be used. I want to match the arguments when the second argument is twice the first one. And if that is the case, I return some value. Okay. So as we have learned last Tuesday, you guys suggest, what are we going to get here? 6. Okay. 3 squared, it's 9 minus 6. Okay, 6. Well, we can say, will it match or not? It's easier. Do you think it's going to match?
Yeah.
Sure. Okay, there is going to be a surprise. Everything matched except for the first one. It looked like the most obvious, and instead it didn't match it. Patterns work in a symbolic way. In this particular case, I'm asking Mathematica to compare two numbers. So actually what I'm asking Mathematica to do is to take 6, divide it by 2, and compare it with 3. But that's not how pattern matching works. Pattern matching it works from a symbolic perspective. The way to accomplish the desired result is to specify a constraint. Now this changes everything, because now I'm imposing a condition between the two arguments. So now I want H to match any two arguments, and then I ask, this definition only works when the second argument is twice the first one. And now all of them will be matched. All right? Do you see the difference? This is now this has been turned into a numerical evaluation. Before it was purely a syntactical comparison.
Is there a difference if we put the constraint after the function name, or if we just make a constraint on y?
Yes, there is a difference, but it's subtle, and I couldn't really find an easy example. Let's see. In this particular case, the constraint operates on y. It doesn't match this x over there. So if you do this, then things become, let's see, then things start working again. Oops, no, they don't. They don't. Yeah, they fine. See, now things start working again. It's subtle, okay? I didn't want to get to this level of detail. Also, you can place the constraint after the definition, but to me it's more difficult to read, so I place it here. All right. What do we have here? We have, well, you guys should help me. What does this function do? What does this pattern match? Let me bring it up. Okay, we have curly braces, so we are in a list. We have multiple elements. multiple entries. Anybody remembers this? Yes, it matches pretty much everything, anything. So we have a list with 2 or more entries. Can it be a list with 0 entries? No, because there are single patterns here. They have to match something. So there have to be at least 2 elements. These can be empty. So this is a list with 2 or more elements. And then the constraint is that the first 2 elements add up to 4. If that is the case, I return the remainder. So I evaluate this, I go here, and oh, look at that, what a coincidence. 3 plus 1 adds up to 4. So what do I expect? Thank you. What do I expect now? 4 and 1. Yes, the first G matches 3, 1, and this is the rest. It's going to be L, and chucks this and returns that. The second G now matches X and Y. Oh, they also add up to 4. Very good. So it's going to be 4 and 1. How about this? Very good, guys. Very nice. So it's not the empty list. It's just that this is not matched by the function definition. So it returns G of 4, 1. Okay, over here I have a little bit of a overloading of a function. So I define the function over the real numbers when they are greater than 2, over the whole real spectrum, complex numbers, and integers. What will this thing look like? Plot. Can anyone guess what it looks like? I see people doing. Yeah?
The complex case will not be shown because we already have built.
Okay, I like that. That's a good start.
Complex numbers, not in this case.
I like this start.
Integer probably also not plotted because plot uses floats. I don't guess it will interpret 2.0 as an integer.
You're getting there. I kind of agree with you. These 2 definitions are useless. Yeah?
The other 2, well, everything we're going to get will be real, so the second pattern would match, but the first pattern will match everything when x is bigger than 2.
Mm-hmm.
Since we define it first, we will get a sign as soon as x is greater than 2, and we'll get a square before that.
Anyway, the x underscore real is more specific, so it applies first. So it applies almost any real.
Why do you say that this is more specific? This goes from minus infinity to plus infinity, right? And that goes from 2 to plus infinity.
Okay.
So yeah, I agree with the analysis. That's what happens. We have a parabola, and then we have a sine. We don't see the numbers, the integers, because the integers are specific points, and you have a probability 0, or almost 0, to hit one specific point when you are traversing, when you're working on a continuous interval. Okay, you have seen this already. We talked a little bit about this last week. What does this match? We have a pattern consisting of 3 pieces. What is this?
Any function.
Function. Any function.
An unevaluated function. So
unevaluated function. Okay, that's fine. Any function or some special function?
That takes 2 arguments.
Yes, any function that takes 2 arguments. And what does it return? It returns the name of the function and the list of the arguments. Yes. So, should we get g comma a comma b? Yes. Should we get sine comma x comma y? But wait a second, sine of x comma y, is it even defined? Very good. So Mathematica complains because it doesn't know what sine with 2 arguments is, but in the end we get exactly what we wanted, sine xy. Okay, how about this? How about this? Oops. Sine of 3 plus pi, oh, it happens to be minus sine of 3. Can somebody understand what is going on?
Yes, there are 2 functions applying to 3. One of them is the sine, and then the negative to all.
Yeah. So this minus comes from multiplication of sine of 3 minus 1. We just hit a point where this simplification is possible. We can understand what really is going on with full form. So now we have times of minus 1 and sine of 3. So our function will return times minus 1 and sine of 3. Okay.
What is times?
Multiplication, product. Okay. This is a trick I showed you already to see what's going on. You can add a print and then you still do whatever you want, but you can use this many ways, and I will show you such a trick in plotting later on. This helps you to figure out, to debug or to figure out what is going on. Alternatively, you can use the trace command that shows you how the evaluation is performed. Okay. So what am I matching here? So it's the same function as before. We still have 2 arguments, but then there is a lonely pattern here, which I wish I could highlight. Okay, that guy. So that is confusing, but if you look at the full form of this thing, now you see that there is times, it's a product of a blank is this guy here, and then a pattern of all the rest. So basically what I'm matching is the same as before multiplied by something. Now I need a factor, and so the function with 2 arguments, okay, it's here, and now I also have a factor, so these will be matched. And I get, oh, match, this is a print statement. See, this is a different type of cell. It's not input, it's not output. And that's the result. Okay, enough for that. Now we move on with different patterns. Now we have optional arguments. Because we love patterns, so we look at all the possible cases. No, not really. We will not cover every possible pattern. So let's read this function definition. We have 3 arguments, a, b, c, and then we have a 4th one with an optional, a default value. This means if the user, if f doesn't get this 4th argument, then just use lower as default value. Okay? What does the function do? Basically, it's defining a triangular matrix. If mode of this triangular matrix is lower, it means I'm defining a triangular matrix. So these 3 values end up being A, B, C in this shape. If instead I'm defining an upper triangular matrix, the 0 ends up down here. And anything else, notice true, which works. I have a test. If it's satisfied, then this is returned. Then I have another test. If it's not satisfied, if it's satisfied, this is returned, and so on until some test is satisfied. True is the final guard, so that you know that this will be satisfied no matter what. And then I say, oh, okay, you have passed the mode that is unknown. So I can say upper, and I define M1, M2, M3. See, this is an upper triangular matrix. I can say lower, okay. If I don't say anything, who remembers what was the default? Here we go. If I say, please define a symmetric matrix, it says, no, no, you're confused. That's not what I do, okay? Okay, I want to give you this example. We have seen this several times already. Power function, a to the power of b. Okay. Does it match or not? No. Yes or no? No. Yes or no? Yes. Yes? If I ask twice, I get different answers. So, why no?
Because it's a function, plus is a function.
Yes, but this will be plus t comma y. So the exponent will be an expression and it will be matched by b. That's fine. It will all be one single expression. So this is okay. How about this? No. So no match, yes match, no match. Now look at some magic. New pattern, and I say, please match anything that looks like a to the power of b. But you know, if I forget to pass b, just think that is a 0. A to the 0 is, wow, a to the 0 is 1. I didn't mean that. Let me do this. Okay. So, do you think this is going to match? We have a no? No. Why not?
Same reason as before.
Okay, I guess I wasn't convincing enough. Now it matches because 1 to the power of 2 becomes 1, and then it tries the pattern and it doesn't find an exponent, and it says, oh, it's no problem, let's just assume it's a 1, and now we do get the match. So this is a way of, with optional arguments, it's a way of extending the patterns to match more than one single type. Okay, one single structure. We can extend them. This is very powerful, by the way. And now I prepared this recap. So this is how you define a function. This is how you constrain a type of an argument. Function with multiple arguments. Function where one argument doesn't have the underscore, it means it's fixed. Function with a test on the argument. Function on a condition on one of the arguments. This is almost the same thing. I'm not sure if there is a real big difference. But the big difference comes here. Now the condition can be on all of the arguments. This is to answer the question that we had before. Now the test is outside. Over here we have a pattern that matches one element, a list, a non-empty list, and anything. Then a pattern that matches a specific structure of the expression. So now we need to have this plus. And over here we need to have this structure. So what do we have? We have a list whose first entry is also a list, and this is composed of 2 entries. Over here I show how to assign names to different pieces of a pattern.
Question.
Yeah.
For this A underscore B underscore underscore, what takes precedence? This B, is this multiple elements greedy or is it not greedy? So if I pass 4 arguments, what would no in the 2 examples before?
Ah,
A, B, L.
this one?
Yeah, is it greedy or is it not greedy?
No, it's not greedy. It tries to satisfy the constraint. So if there is an assignment that does not satisfy and there is another that does satisfy, it will match the one that satisfies. If more than one is satisfied, then it's from left to right.
Can we have B and L in the same definition?
Yes, sure, yes.
Okay, so
Then B will get everything. Then that's what you mean by greedy. Yes, B will catch everything. I believe. You guys are interesting. That's K equals B. Yeah, right. Exactly the opposite of what I said. Yeah, so it catches the minimum. So not greedy at all. All right, then these are the standard 30 seconds that you remove, right? Okay, assigning names to different parts of the patterns. And over here, default argument. If B is not passed, then the value of pi will be used. Okay, enough of this. Questions? How are replacement rules used? So all of these patterns that I have shown you can be used as part of a function definition, but they can be used also as part of replacement rules. Remember replacement rules? So we have some expression or a list, something, and then I say if something, then replace it with something else. In that if something, we can put any of the patterns that I have explained in the last 2 hours of lectures. Okay, for instance, here we have a logarithm, and we all know that the logarithm of the product is the product of the logarithms. Here I'm defining my own logarithm. How do I see that? It's not capital L. Had I used capital L, I would be working with Mathematicas logarithm, so that would be a completely different story. Okay, doesn't do anything. But here I'm working with my own logarithm, and I want to decompose it. So I want to say, every time you find a product, please split it in 2 different function calls. So does it make a difference if here I have A and B, or X or Y? Could I write this? Is it any different from what it was before?
Only insofar as now you cannot use any other x and y. So if you were to define an x somewhere and try to use it in there, you would get the argument and not
Yeah. No. Okay. We don't have any. There is a clear slate right before this, and there is an exit right after this. So is there any difference between having A and B here or X and Y? No difference, okay. And here it is. So X matches A, Y matches B times C times D, yeah?
Can I see the full form of logarithm of ABCD? Is this a multiplication of 4 things? Or
Yes.
is it some kind of power?
No. It's times A, comma B, comma C, comma D.
Okay, and how can the replacement rule match? Because it matches on a multiplication of 2 things, and this shouldn't match on a multiplication of 4 things.
Aha.
Because I would have written y underscore underscore.
Aha, it's not a list. This is a product. It's b times c times d. It's not a list. It's simply times of b, comma c, comma d.
This is again nothing with sequences.
Exactly, it has nothing to do with sequences. What you're thinking of is something like this, and with comma, with something like that. That would be entirely different, okay? This would not work, okay? That's what you're thinking. But now we're talking about expressions, and so that's good.
I'm thinking it's matching the structure, and it sees times AB times XY, and tries to match that on times ABCD. So it should have problems matching this this 4-element thing to the 2-element thing.
No. It doesn't have any problem because it matches the first entry with A and then times of BCD with Y. So this works perfectly, but that's not what we want because now we have this thing that is not broken down yet. So now we need a repeated replacement rule, double backslash dot, and now I really break down my function. So this is an easy example with logarithms. You can define your own integration rules. You can define your own cost function. You have a program and you want to say how expensive is my program, maybe in terms of operation counts, and you say the cost of the program, and you replace it, it's the same as the cost of the for loop plus the cost of the body of the loop, or it's and you give all these rules to break down something big in terms of the modules, in terms of the bodies. Okay, Mathematica uses, yes?
Does it, if you write log times A, comma B, is it the thing? No, not there on the pattern matching file. If you, no, times, if you use this as the function times explicitly.
Yeah.
Yes. Okay.
They are absolutely identical.
So it's not enough to know that times ABCD is the same as times A times
Yes.
B times C times D.
Absolutely. These are all algebraic simplifications, yes. So replacement rules are used by Mathematica, for instance, to give solutions to equations. Here we have a polynomial. Let's plot the polynomial. I told you already how to plot functions. You just pass the function with an argument, then you bind the argument, and you fix the intervals. By the way, it also works for 2D functions. Now we would have plot 3D. We would bind it to both of them, and we would have two iterators, so two intervals. Okay. So what I want to do is to compute the maximum and the minimum of this function. And I will just use Mathematica for this. So what do? I derive the polynomial, I compute the derivative, set it equals to 0, and then I solve it. So I just go easy, okay? I don't do anything smart. And Mathematica gives me the solution with these replacement rules. In fact, it solves it symbolically, so there is no approximation made. And okay, I know that the maximum will be either here or there, and the minimum will be the same. Now I can see if actually it's true that the derivative is 0. So now I say this is the polynomial, so this is exactly this object here. And now I apply these replacement rules. So here it says apply the replacement rules, and then I pass the replacement rules. I told you that if you have a list of replacement rules, and the replacement rules have to be separated, then you will get a list of outputs. So I expect to get 2 outputs there, and hopefully both of them are zeros. Yes. Now I look at the value of the polynomial. Now I'm not looking at the derivative anymore. I'm looking at the actual polynomial. Okay, this doesn't tell me anything. I don't really know which one is the maximum, which one is the minimum. So I pipe with n, and I see, okay, the maximum is that, and the minimum is there. And we will do more of this when we get into visualization. Now, another way of using replacement rules is, or actually I should say, another way that replacement rules are used in Mathematica is with the options for the functions. This is a parametric plot. Is you see capital P, so this is an internal function, and it takes it's a 2D, otherwise I would have to say 3D here, but so you know, you expect already something in 2D. So I pass 2 coordinates, x and y, and they both are expressed in terms of a parameter, and I vary the parameter from 0 to 100. What I get is a spiral. Okay, and now I want to be artistic, and I want to change this plot. So first of all, I look at the options available, and there are gazillions of them. If you look at them, not all of them, most of them are replacement rules, okay? Arrow, arrow, arrow. So now I want to change some of these options. What I have to do is define my own replacement rules. So I'm going to use fewer plot points. I will eliminate the axes and so on and so forth. So normally the arguments stay the same, and then you have a list of options. You see that the argument is the same, and then from a point on you just have the list of options. It doesn't matter in which order you pass these options. It doesn't matter how many you pass. These are just replacement rules, so you know how they will be evaluated. And this is what I get. Okay. So if you want to use the same structure when you define your own programs, what you should do? Well, you're writing a program or a function, and you decide which options it will accept as input, or it will use. And you will define some default values through the function options of program. Notice that this is, I define this, okay? Then you write your program or your function, whatever, and it catches a list of options. Notice the triple underscore. Why triple? Because maybe I don't want to pass anything precisely. It doesn't have to be mandatory. If I pass something, okay, I have all my definition, and then I take into account the options that I pass, and then if some of these options, if some of those options are not defined, I better catch them from the complete list of options. So these options, these rules here, will overwrite the defaults. They come first. And if they don't cover everything, you go and fetch the options from your definitions. Questions?
Is there a data type for replacement rules? So I can say that these options really only captures replacement rules?
No. But you can do, I mean, there is not a data type, but you can force this to have, it's one of the patterns that I didn't show, of course. You can force this to be a replacement rule, and then there is a way of saying that it's a list of such patterns. So you can define your own data type, for instance. That's what I normally do. If I want to pass a matrix of matrices or a list of matrices, I define that data type, and then I check the pattern. You put a constraint and you say, is this such a data type or not? Okay, guys, let's have some fun, I hope. Let's do some sorting. So over here I create a list of 8 integers, and I want to sort them through replacement rules. Okay, here is my first attempt. I say, L is the list. Please find numbers, pairs of numbers, such that I want to sort this list from the smallest to the largest. So I say, every time you find A which is greater than B, please swap it. Yes?
No, because this would compare one element to the rest of the list.
Will it? Will it really do that? It's close, but not quite.
This is not the same case as the times before.
That's right.
It's lists again.
This is your case. This is your case. This B doesn't match the rest of the list because it only has one underscore.
But this can match sublists, subranges of lists.
Yes, it can match sublists. Yes. So, do you see any problem with this?
Yeah, I think this just will do the job one time. Don't we have to use a double slash?
I like this comment, but is it true?
I think it will create lists, comma, another list. So it will not just create one list, it will create a list of a lot of lists.
Well, before getting there, let's talk about this. Is it going to match something or not? Who says not? Why not?
Because here's only 2 elements in the list and we have...
Very good. I am fixing the list to have 2 elements. I don't have double underscores. This thing will not match anything. List didn't change a tiny bit. So over here, I try to be a little bit smarter, and I say, okay, let's put something on the left, something on the right. You're still not happy. Why not?
I know what this does in regular expressions. This will discard everything before and after the match,
Mm-hmm.
and will not reuse it in the result on the right side. So we would have to name
Ah,
triple underscores and reuse them in the result.
that's a good point. So what will we get out of this?
List of the numbers. If all.
Which ones, if at all?
I don't know.
First 2, so it would be 10, 12? Yeah, so it stops here. Okay, how about this one?
This will create a lot of instances of the list. It will not just do the,
Why?
it will do the left, comma, B, comma, A,
Yeah.
comma, right, then, okay,
How do we know it will vary how much is put in the left and right side list? Because maybe it doesn't know we want to iterate over all combinations.
Yes, it does. It knows, because it's a double slash. Yeah?
But it will always make the left empty
Yes.
Mhm.
because it's not really.
It will iterate as long as something changes,
Yeah.
but it doesn't know how to distribute the elements of the list
It doesn't matter.
into our map. Yes, it does.
You just need to find 2 that are in the wrong order and put them in the right order and keep doing that. As long as every
It
step
matches
you
first.
sort the list more.
It matches the pattern first, and then it uses the guard and tests. It doesn't know that
So
if
either
the
it
guard
works or it
fails all the
doesn't.
time.
You try again.
That's right.
So, the point is, it doesn't matter in which order you match these A and B, as long as there are 2 successive elements, adjacent elements, that are out of order, it will keep swapping. It doesn't matter if you swap the first 2 or the last 2 or something in the middle. It will just find that 2 elements are not sorted. And if they are not sorted, it will swap them. And then it will check again, and will check again. So what you might be confused by is the complexity of this. And we make no claims that this is a smart way of doing sorting. In fact, this is by no means better than a quick sort. But this is a sorting algorithm.
by matching those places again?
No, 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 no. This is a double slash.
A
So
greater than B. This has to influence what matches on the left side, on the pattern. Because if the A greater
wait. So here we have a list, an input,
Yeah.
and this is what will be replaced with.
Yeah.
Okay? Now, if we only have that, the replacement rule is applied once. So we have an input and we have an output. Okay, and that's the end of the story. Once we have the double replacement, the output all of a sudden becomes input for the next iteration.
Yes,
But isn't it just compare the first two entries over and over again?
No.
Left is empty.
Why I would do that? You are giving left and right the possibility to vary from empty to n over minus 2, where n is the length of the list.
So in this repeated replacement operator, it knows to vary those kinds of patterns.
Yes.
Okay.
So, but it's not in there. It's the pattern that does that. It doesn't. That thing only means that you are applying the pattern multiple times. The important thing is these triple guys, and they will. This is what I tried to say before. They will be changed in all the possible ways to see if there are two entries that satisfy that condition.
I think I know what they're saying. I think because most of the times the data structures have empty before every list and empty after every list. So they might think that it might match empty every time.
But that emptiness, you always have to think in terms of constraints. The constraint here is to find two numbers such that they are adjacent, one next to the other, and in the wrong order. So I pass the 3. Okay, maybe we can do this. So how does this? Let's see if this creates problem. Yes. So what do you guys think is going to happen now?
It will sort all elements but the first and last.
But the last is sorted already, so we will have a full sorted list. A full sorted list except for the first two elements. Precisely. So you got it. We have a full sorted list except for the first. Why? Because we're not allowing left to be empty.
What if the last element isn't sorted either?
Yeah, it's not going to be sorted.
Okay.
It's going to stay unsorted. There is a way of figuring this out, and I have an example just a little bit later on. So the next example will help you. Okay, now I want to find the two successive entries such that the second entry B is the first plus 2. And this is how I get it. So replacement list, and I say, okay, there are A and B equals A plus 2, so okay, I just return B and it terminates. Complaints? Same story as before. I'm doing the wrong thing here. I'm trying to match these two elements, but I fixed the length of the list to be 2, so this is not going to match anything. Okay, now I give some more freedom. I say L1 can be anything, L2, L3, okay, that's what I want. If L3 equals L2 plus 2, then please return L3. So I'm finding the first number, which is 2 plus the previous one. So what do you think is going to come out of this?
On the first iteration.
What did you say?
First iteration will, so one iteration will be here.
Yes, but what's the output? Somebody said 8, right?
3 maybe?
No, just
That'd be fine.
because it's only one step.
Three. It doesn't return, well, it returns. Okay, so what is going to be? What do you mean 4? We are saying that L3 is L2 plus 2, so how can this be 3 plus 2?
Yeah, but if L1 is empty,
Yes,
so 1 and 3 will
yes,
also match this,
yes,
and then we will get L3. So,
which is 3. So we will get the list with 3. Yes. Now, what if I wanted to get all the entries, and now we go back to your problem before. I don't want to see just one match, I want to see all the possible matches. So I don't want just the 3, I also want the 6 and the 8. No, not double slash. No. Not double slash.
Okay. Then we have to concatenate every time the list will.
Very good. You would have to do some operations. Here I'm simply returning L3, so definitely not. That's not what I want. Maybe I could do L3, comma L4, but this is not going to work. Yeah.
We could use 3 different replacement rules. The first one takes a simple list and wraps it in another list. The second one
Yeah.
does what we're doing. The third one,
Probably you could, but there is a command to do that. It's called the replace list. So it gives all the matches. Now we have a list as input. That's our left-hand side here. And then we have the list, the replacement rule. And now I don't get only one output, but I get all the possible matches. And if you did this with the sorting, actually we can do that. We just have to change if L2 is is greater than L3. Return what do we want? L3 comma L2. Oh, it's sorted. Ha ha ha. Put a 5, 2, 8, 6. And I get all the pairs that are matched that are not in the right order. This is at one iteration, okay? Then one of them will be swapped. This is not how the sorting was working before. It's just to show that these L1 and L4 are used in different ways. And as I'm saying, this replace list is very useful for debugging because it shows all the matches, all the cases. List analysis. Okay, let's find all the sequences whose left and right elements add up to 6. So we have a list and we want to identify the subsequences. Now we're clearly getting into genome studies and stuff like that. We want to find all the sequences where the left and the right entries add up, combined together, add up to 6. There are several of these things. Okay, this is the input, and then I say, I want to catch some sequences where L1 and L3 add up to 6. If that is the case, please return L2. Are you happy with this? Oh, already.
I actually have a better thing to do from the beginning. It's completely different. Which is just to do A1, comma, 2 underscores, comma, L2.
L1, 3 underscores.
No, L1 underscore.
Oh, underscore.
Comma, 3 underscores, comma, L2. And the rest is
The rest is out, and you're saying this.
L1 and L2 equals 6, then then
Okay. LL. Okay. I kind of like this. Let's look at it. It's no. Can you guys help me? I think you probably know. Let's see if anyone else knows.
Because this will match first element and last element to the list and everything else to the middle list. So 3 and 6 are 9 and not 6.
So this L1 has a single underscore, so it can only match the first entry. Likewise, L2 will only match the last entry. And it just happens that 3 plus 6 is not 6, so we don't get much. But of course, this is the first idea that comes to mind. I agree. How about this?
It will probably output 6 lists. At least 6 lists.
Okay, do you think it's gonna work or not?
Yes. Of course.
No?
I'm
Because
confused with this too.
it matches the first 3 elements, then
Yes?
3, 6, and 1, and they match, but they get nothing.
Yeah?
If it happens, for example, like 4, 3, and 2, then it will match.
Yes?
It will come out 3.
Yes?
Then, yeah, that's it. And 0 and 6, it will come out with another 3.
Yes? So it looks like it's working. That's right, that's right. So as long as there is at least one element in between the extremes. That's right. So I think, yeah?
We're not exactly doing what we said before. We want to find all the sequences whose left and right elements add up to 6.
Mm-hmm.
It could also be the sequence 3, 3, if we had one in there. I don't know if there is one in there, but we require that there is something in between the left and right element in our function.
Yeah.
Or replacement rule, which is not required by the sentence that says what this thing is supposed to do.
Yeah, okay, maybe you're right. I should,
Want to return the whole sequence.
yeah, I should probably rephrase it or, yeah.
And there's a third thing that happens. We could have a sequence 6, 0, 0, which would also become a problem because effectively, in the end, when we want to do something like 3, we can also consider that a sequence, just 3. And if we take the left element, which is 3, and the right element, which is 3, we get a 6 again. Which would also
Okay, let's move on. Let's do something useful. Next example. I want to do some encoding. So we start from a list. Our list only has 2 entries, 2 characters, 2 symbols, A's and B's, and I want to compress it. So since I have a sequence of 4 A's, I want to encode that A, 4. Since I have 2 B's, I want to have B, 2, and so on. If we have very, very long sequences, you can imagine that these would compress the list. Okay, so here is a way of generating random lists with the 2 symbols, A's and B's. This is not how I would define it. You will see how I will define it not today, another time. But this actually works, so let's see. If I do rand L of 5, I get a sequence with random B's and A's. Rand of 15, here we go. And now the idea is to go through this list and find common adjacent elements that have adjacent elements that are equal, compress them and increment this value. Okay, how to do that? First of all, we do this and forget about what it is. This simply transforms the list, attaches a 1 to each entry of the list. I will explain this in details later on. So what this does, where is L? Ah, that's why. So now I have the starting sequence. It's just that I have a 1 attached to each entry. And now I want a replacement rule that looks for adjacent numbers, adjacent pairs with the same character. So help me with this, please. LL, no, where is it? LL. Okay, what do we want to do?
Left, triple underscore, comma, x, oh yeah, yes. And then we have to use two lists again, the structure. Let's call this x underscore, comma, y underscore.
Nah, it's a number. Don't use y for numbers. N.
Okay.
Very nice. I like N1. But here I use N. So I put N. How about here? Then it could be this. Yes, absolutely. But the truth is that I will never put anything but integers there, so let me keep this short. But yes, absolutely. You're right.
Okay, and another list of x without underscore and m underscore.
Without underscore and M underscore.
Some other way. This goes to left, x, n plus m, right. Yeah.
Okay, is everybody happy with this? No? Come on.
I think you need the underscore under the second x.
Absolutely, I agree fully. We are still on the left-hand side of the rule, so we are still working with patterns. So we need to put underscores. Other complaints? Yes?
Maybe we need a double backslash.
Ah, yes. Probably we do need a double backslash because we want to keep applying this until nothing changes. Wow, that was a crappy sequence. Yeah. So A4, B3, A2, B1, so on. Looks like it's working. Do we need the 3 over here? Yeah, we do. Let's see. Otherwise, we would have A1, A1. So we definitely need that. Very nice. So we have 10 more minutes. 10 more minutes. 10 more minutes. 10 more minutes. Visualization. No. Functions or visualizations? Functions? Functions. Okay. So we have 10 minutes of more functions. Now we get into pure functions. This is really cool. You can define functions on the fly without assigning a name to them. This is super cool when you want to write cryptic and unreadable code. Also, when you want to write code that is as short as possible. Remember, there will be a competition to create the shortest code. This is super cool. Okay, this is how to do it. This is a pure function. It doesn't have any name. It takes an x, an argument x, and it spits out the argument square. The function doesn't have any name, okay? So the only way to use it is to pass an argument right away. or you assign it to something. Let's say right now this returns a function, so doesn't return any value, it returns the function definition, but I cannot use it. If I pass an argument right away, I get a 9. Okay, here is here is a function definition, and I assign it to this guy f1. And now I can use f1. At this point I do pass arguments to it, and I use it to plot whatever f1 is. As I said before, now we have 2 arguments, so we go into 3D, and we will have 2 iterators. Here we go. Okay? Nice and easy. But we have written a lot of characters. We can certainly do much better. This is the square function. Now we don't have functions, we don't have input arguments, anything. We just have hash squared. This is the argument. How do you know that this is the function body? Because it's before the ampersand. So this is a function body. This is the argument. This is stops. That's the end of the function definition, and this is the call. So the actual argument. If I evaluate that, I get 9. If I evaluate this, I get that was a good one. Okay, the first question is, what is A? A is a unevaluated. So what am I going to get? Precisely. But it orders, anyway, yeah, a cubed minus a squared. Now I want to pass more arguments. Then I identify the argument by number. Hash 2 means second one. Now I have to pass 2 of them, and this will be 3. Yes. This will be, yes, this is an error. This is really an error. It doesn't like it. Okay, then if we have a lot of arguments, this thing catches all of them. Notice how I put them into a list. Otherwise, I would have the sequence. Remember the sequence? We don't want to talk about sequences. So now I have a list. So what am I going to get out of this?
The list for 6.
Very good. So this thing here catches all of the arguments. Then we put them into a list, and we multiply them by 2 for 6. Okay, here is a way of plotting some function. Which function is cosine plus sine? So which function is that? Precisely. Cosine of hash number 1, here is the function call. So first argument is x, cosine of x plus sine of both of them. So it's x times y. I pass 2 iterators here, and so it's going to be a plot 3D. This is the exact same plot as this. Okay? Okay, what's this? This is fun. It returns a function. Very good. As an output value, I have something that ends with the ampersand, and as an hash, this tells me that it's a function. H is a function that takes whatever and an integer and returns whatever evaluated. It's actually evaluated with nothing, to the power of k ampersand. So it's a function, unevaluated. It's something that we will be able to evaluate later on. So h of sine of 3, what is it going to be? The third power of the sine function, and now I can evaluate this. This is the second power of the sine function evaluated in 1.3, and I compare it with this thing, and oh, look at that, they are exactly the same. Okay? What am I plotting here? Sine of x, 2 times, not really.
Sin x, x sin x square, and x sin x.
Yes, I'm plotting x sine x square sine x square, and x cubed sine x cubed. These are these guys. Okay. And over here, I am doing a similar thing with a table. I am generating a list of functions, and I am evaluating all of them in x. I varies from 1 to 3, so I will get the exact same thing. There will be a tiny little difference. Let's see if anyone catches it. Discrete? What do you mean?
It's a discrete function.
Oh, no. I'm going to get the exact same plot with a really, really tiny little difference. Did anyone catch it?
No colors.
That's true, no colors. So this thing here, they were 3 functions, and this is actually one object, so it's all plotted in, but let's not get into that. Okay, I think it's enough for today. See you guys.